All right, buckle up. We're going to go through the entire Unit 8 study guide. So this covers equilibrium, kinetics, acids and bases. It's going to be a lot of fun. All right, question number 1 says, consider the following reaction. Identify 3 ways to increase the rate of reaction without adding a catalyst. Explain how each would impact the rate using collision theory. All right, well, first way is we can increase the temperature. If we increase the temperature, this is going to increase kinetic energy. Remember, kinetic energy is energy of motion. So molecules, can't spell, move faster and are more likely to collide. Okay, so remember, the big point of this unit, we need to have collisions with the right orientation and the right amount of energy for a reaction to take place. So if we increase the temperature, that's going to cause the molecules to move around faster, and it's going to increase the likelihood of a collision. The second way is to increase concentration. So if we increase concentration, there are going to be more molecules available in the same volume. So that's going to increase the chance, so more likely to collide. So think about a classroom. There's 2 people in a classroom, and they're moving around. The chances of them bumping into each other are pretty low. But if you had, 100 people in the same little tiny classroom, you're probably not going to be able to move without bumping into somebody. So that's an analogy for how concentration affects reaction rate. The final way is to increase surface area. So when we do this, this provides more exposed molecules available for collision. Okay, so when we do this, we're basically going to break apart, crush, whatever, so that more of the substance is exposed and available for collision. Okay, so you've probably done this. You've probably made, hot chocolate. If you had a Hershey bar and you were trying to dissolve it into milk, it's going to take a really long time to dissolve, but if you break it into smaller pieces, it's going to mix a lot quicker. So kind of the same thing happens here with surface area. So more collisions, faster reaction. Oops. And one other thing I want to mention, pressure or volume is not an option since neither reactant is a gas. Okay, so if you look at the reaction here, we got a solid, we've got aqueous, we have a gas over here, but on the reactant side, these two neither are gases, so yeah, pressure volume doesn't really apply here. All right, moving along. Number 2. It says, in 2 different experiments, equal moles of zinc and equal volumes of hydrochloric acid are reacted. After 2 minutes, the volume of H2 produced is recorded as follows. It says, explain why the rate of hydrogen gas produced in experiment 1 is greater than the rate in experiments 2 and 3. Well, let's take a look here. So remember, surface area, so the first column that we're looking at here, surface area is going to increase the reaction rate. So in experiments 1 and 2, it's powdered. So it's more likely to react because more surface area is exposed. Okay, what else do we have? In experiments 2 and 1, the concentration is a lot higher than 3. And as far as temperature goes, temperature is higher in experiment 1 More temperature, things are going to move around a lot quicker. And volume, remember, smaller volume is going to cause the reaction to happen quicker. So it's like the molecules are bouncing around on the football field or like a closet. Okay, the chances of you bumping into somebody on a big football field pretty low, but if you take the two people and you put them in a closet, again, you're not going to be able to move without bumping into somebody. So when you constrict that volume, it increases the chances of a collision. Okay, so for A, it says explain why the rate of hydrogen gas produced in experiment 1 is greater than the rate in experiments 2 and 3. Well, I goofed a little bit because I was looking at the volume of H2. That's what we're producing. So we're making more here in experiment 1. If you were reacting things and they were in a smaller container, my analogy would hold true. Okay, so explain why the rate of hydrogen gas produced in experiment 1 is greater than experiments 2 and 3. So a couple reasons why. So one reason why zinc is powdered. So greater surface area. Concentration of HCl is greater. And the temperature is the highest of the three trials. So we kind of went through those three things. Zinc's powdered, concentration of HCl is 10 versus 3 in experiment 3. And then the temperature is 15 compared to 10 for experiments 2 and 3. All right, it says, which two experiments are the best to test the effect of temperature on the rate of the reaction? Well, let's go back and let's take a look at this. So if we're just testing the temperature, that should be the only thing that changes. So if you look at experiments 1 and 2, they're both powdered. We have a concentration of HCl of 10. The only thing that we're changing is the temperature. So experiments 1 and 2, because temperature is the only variable that is changed. So the surface area and the concentration of HCl stay the same. The only thing that's changing is temperature. How would an addition of a catalyst change the rate of reaction? So a catalyst. Let's see. We've got like when you were little and you were riding your bicycle, you had a hill that you were trying to pedal over. You know, a big hill like that is going to take some time. It's going to take a lot of energy to get over that hill. What a catalyst does, a catalyst lowers the hill. So instead of it taking, 10 seconds to ride your bike to the top and go over the hill, it only takes 3 seconds. So the reaction happens faster and requires less energy. So it lowers the activation energy and increases the rate of the reaction. All right, moving along. Number 2. At 40 degrees, hydrogen chloride gas will form from the reaction of gaseous hydrogen and chlorine, according to the following equation. Using the data provided, calculate the following average rates. So let's see, it says disappearance of hydrogen gas in the first 2.16 seconds. Okay, so we're looking at hydrogen gas, which is right here, and it wants the first 2.16 seconds. So we're going to be looking at those two concentrations, and we're going to be looking at those two times. So rate is equal to the change in concentration over the change in time. So concentration goes from, at 2.16 seconds, it goes from 0.5 to where it started, which was 1, over the time, 2.16 minus 0. Okay, so when we do our math here, 0.5 minus 1 is going to give you a negative 0.5 over 2.16. So that'll give me a rate of negative 0.231 molarity per second. So if it's disappearing at a rate of 0.231 molarity per second. Appearance of hydrogen chlorine gas in the first 4.32 seconds. So here's our chlorine gas, and we're looking at the first 4.32 seconds. So we're going to be looking at these two time points, these two concentration points. So the change in concentration, so it goes from, let's see, we go from 0.25. Oh, I goofed. I picked the wrong numbers. It's hydrogen chlorine gas, so it should be, these two numbers. I was looking at just chlorine gas. We want hydrogen chlorine gas. Read the question carefully. All right. So it would be 1.5 minus 0 over 4.32 minus 0. So essentially we're going to do 1.5 divided by 4.32, which will give us 0.347 molarity per second. That's the rate of appearance. Okay, now we're moving on to chlorine gas. So we're looking at chlorine gas. It says between 2.16 and 4.32. Okay, so it's going to be 0.25 minus 0.5 over 4.32 minus 2.16. And you should get a negative 0.166 molarity per second. So it's asking about the disappearance, so that would explain why this is negative. So we're losing 0.166 molarity per second of chlorine gas every second. Okay, consider the following data collected from a lab during which the following reaction was performed. Explain the change in reaction of the 4 trials. All right. So let's see here. All right. So looking at the data, the fastest reaction was this one right here. The slowest reaction was number 4. So we have NH3, and we're adding water to NH3. So if you look here, 25, we're not diluting at all. We're not adding any water to change the concentration of NH3. Trial 4, we are diluting it. So we're only using 10 milliliters of NH3, and we're adding 15 milliliters of water. So there's more water than NH3, so it's really dilute. So let's summarize those points. So trial 1 was the most concentrated. So it had the fastest reaction. Trial 4 was the least concentrated, so it had the slowest reaction time. So again, if you look at the volume of HCl, it's the same for all 4 trials. The only thing that changes is the concentration of NH3. The first trial, we're not adding any water to it. It's not dilute at all. Trial 4, there's more water than NH3, so it's really dilute. So that's why it has the lowest concentration. Okay, write an equilibrium expression for the following. Okay. So let's just recap here what an equilibrium expression is. So KEQ, our equilibrium expression, is going to be equal to products over reactants. Another important thing that you need to know about this is pure solids and liquids are excluded. Pure solids and liquids excluded. All right. So part A, they are all gases. So our KEQ is going to be products. The only product that we have is NH3. NH3. And we have a 2. That 2 coefficient becomes a 2 exponent. Our reactants are N2. And then we have H2. If you have more than one product or reactant, we multiply them together. And then we have a 3 here. So that 3 becomes a 3 exponent. Done. Okay, in B, we have a solid. So this solid we don't include in our expression. So KEQ is going to be equal to products, ICl. And we have a 2 here, so that becomes a 2 up here. And then we have Cl2. Done. Okay, we have just the solid here. We have a liquid here. So the only one that we have is a gas. So KEQ. Products, so N2O. Over reactants. We don't have any. So that would just be over 1. So just writing it as N2O would be it. Okay, number 5. Calculate the equilibrium constant. Does this favor the reactants or the products? Okay, so here is our reaction. So we've got our one side here and that side there. So it's going to be products. They're all gases, so products. So CO is 0.0092. And H2O, 0.0092 over, the reactants. So CO2, 0.1908. And H2, so 0.0908. No coefficients. Okay, when you plug this in your calculator, you're going to get 4.9 times 10 to the minus 3. Since this is less than 1, KEQ is less than 1, it's going to favor the reactants. Okay, number 6. Reaction initially contains 0.75 molar of HI. At equilibrium, the concentration of I2 was found to be 0.3 molar. calculate Kc given the reaction, and there we go. Okay, so when you're working these types of problems, I would suggest you go with your equation for what it's asking you to find. It's asking you to find Kc. Kc is going to be products over reactants. Okay, so we want to be able to plug into that eventually. We're going to need our equilibrium concentrations of everything. Unfortunately, the only one that it gives us, the only value, is the one for I2, iodine. So we're going to need to do a Rice table to figure out everything else. Okay, so R stands for reaction. Our initial concentration is, let's see, 0.75. It doesn't give us initial concentrations for these, so those are going to be 0. Reactants go down, products go up. We have a 2 in front of our HI, so this will be going down by a factor of 2x. These two will be going up by a factor of x, no coefficient. E we combine. So it's going to be 0.75 minus 2x. This will be x. This will be x. All right. Now, at equilibrium, it tells us IUM. It tells us I2 is equal to 0.3. So I2 is equal to x, which is equal to 0.3. So now that we know what x is, anywhere there's an x, we can substitute in our 0.3. So that would mean that H2, which is also just x, is going to be equal to 0.3. And HI, we have to do a little bit of work here. 0.75 minus 2, 0.3. Do the math here, you get 0.15. These are all concentrations, so our units will be molarity. Now we can plug into the original thing that we were trying to do, which was Kc. Products over reactants. So H2 and I2 over 2HI, so it'll be 0.15. And because we have that 2, talking about this 2 right here, this is going to be squared. You should get 4.0 when you do the math here. Okay. A reaction initially contains 2 molar I2 and 2 molar Br2. At equilibrium, the concentration of Br2 was 0.33 molar. Calculate Kc. This is exactly like what we just did. So we're going to need the equilibrium concentrations of everything. So let's go ahead and let's just skip ahead to our Rice table. We know that we're going to need to do one of those. And the reaction is I2 plus Br2. And that goes to 2 IBr. It tells us in the question that we have these initial concentrations. Does not give us an initial concentration of our IBr, so we'll just put a 0 in. Reactants go down. No coefficients, so it'll just be minus x. We do have a 2 in front of our IBR, so this will be going up by 2x. And then we just combine everything. So 2 minus x, 2 minus x, and then 2x. In the question, it tells us Br2 at equilibrium has a concentration of 0.33. So at equilibrium, Br equals 0.33. So that means 2 minus x has to be equal to that. I would subtract 2 from both sides and then divide by -1. You'll get 1.67. That's going to be equal to x. Anywhere there's an x, we plug in now. So I2, 2 minus 1.67 equals 0.33. And then IBR is equal to 2x. Let's plug in what we've got. So we're plugging in 1.67. So we get 3.34. All right, so we've got that, and we've got that. Now we can plug into our KEQ expression. Products over reactants. So IBR2 over I2 times BR2. So 3.34 squared over 0.33, 0.33. And when you do the math here, you should get 1.0 times 10 to the second. Okay, tell me this isn't the most fun you've ever had. Number 8, for the reaction, gives us a bunch of numbers. Calculate KEQ. Does this favor reactants or products? Okay, so it gives us all of the equilibrium values. So for this one, we can just plug it right in. Products over reactants. So this will be NO2 squared, because we've got the 2 here, over NO squared. Again, we have a 2 here. And then O2. Okay, let's plug in what we've got. So NO2, 0.129 squared over NO, so 0.106 squared, and then O2 is 0.122. All right, when we do the math, you get 12.1. It's greater than 1, so KQ greater than 1, so it's going to favor products. Okay, now we're going to move into equilibrium and Le Chatelier's principle. Number 9 says the reaction of carbon, disulfide, and chlorine is as follows. Pressure of the system is doubled. Pressure has to do with moles. So on the left side of our reaction, we have 4 moles. On the right side, we have, looks like 2 moles. It always goes to whatever side has fewer moles. Okay, so it's going to shift right as pressure increases, volume decreases less space favors the side with less moles of gas. All right. CCl4 is removed as it's generated. So that would mean the concentration of this is going to go down. So we have a saying, this will help you in many cases. So if you add, you're going to shift away. If you subtract, it stays. All right, so CCl4, we're subtracting from the concentration. So that would be, it stays on the same side as what we're subtracting, which is the right side, so it's going to shift right. Concentration of CCl4 decreases, so equilibrium shifts right to produce more CCl4. Heat is added to the system, okay? Heat is added to the system. Our delta H value is negative. Since it's negative, that means we're going to have heat on our product side. We're releasing heat. Heat's leaving our reaction. We're adding heat. It's going to shift away. So it's going to shift left. Use up, oops, can't spell. Use up the heat that was added. So again, it follows our add away, subtract stays secret to solving these types of problems. All right, let's take a look at another problem like that. So let's take a look at number 10. So we got a reaction, and it says list as many ways as possible to increase the amount of NH3 produced. Okay. Well, let's see here. So we want to shift right. For it to shift right, that will mean that NH3 is going, more NH3 will be made. Our heat is endothermic, so that means our heat is going to be on the left side. Okay. And the only other thing that we need to do really quick is just count up moles. So we have 7 moles on the left. We have, looks like 5 moles on the right. So we want to get it to shift right. So let's see. To get it to shift right, we would want, for heat, we would want it to add heat. So increase heat will cause the system to shift to the right away. If we increase pressure, we'll shift to the right because there are fewer moles. Oops, fewer moles on that side, 5 versus 7. Let's see, what else could we do? We could increase our concentration of N2. It will shift away. Shift to the right, away. We could also increase our concentration of HCl. That's also on the left, so it will shift to the right, away. On the right side, we could decrease. We could decrease our concentration of Cl2, which will cause it to will stay on the right. Okay, I think that's it. We wouldn't want to do anything with NH3 because we're trying to increase the amount of our NH3, what's being produced. All right, 11. Consider the reaction below. The molarities are as follows. Which direction will the reaction proceed to establish equilibrium? Okay, well, we need to find our K expression. So let's set. All right, so our expression is going to be Kc is equal to products over reactants Okay, products are SO2 and Cl2. Reactants are SO2, Cl2. So let's plug in what we've got. SO2 is 0.035. Cl2 is 0.08. And our SO2 Cl2 is 12. So when we do that, you get an answer of 2.3 times 10 to the minus 4. Now, it said which direction will shift, and it gives us a KEQ. Okay, so Kc is smaller than KEQ. So products, the concentration of our products, needs to increase. We need a larger numerator, so reaction will shift right to make more products. All right, number 12. Consider the following reaction. Which direction will the reaction shift if Cl is added to the system? Okay. This is an ion, Cl minus. If we add it to the system, it is going to bond with what? Well, it's going to bond with our Ag, our silver. Chlorine is -1, silver is +1. So, well, first of all, Cl minus will bond with Ag plus. So the concentration of silver, Ag, will decrease. It's being taken out of the system by an external ion. So equilibrium will shift right to produce more. So when you have an external ion that comes in, it's going to bond with something. In this case, chlorine is bonding with silver. Silver gets taken out of the reaction, so we're subtracting the concentration. And when you subtract, it stays. So silver's on the right side, equilibrium's going to stay on the right side. There you go. Let's do another one like that. It says, consider the reaction. Which direction will the reaction shift if magnesium +2 is added to the system? Well, magnesium's going to bond with our sulfate, SO4, 2 minus. So Mg will bond with SO4 to decrease the concentration of SO4. Equilibrium will shift left to produce more SO4. Okay, so we're subtracting SO4. Concentration's going away because magnesium is bonding with it. Subtract, it stays. So SO4 is on the left. If it is removed, equilibrium will stay on the left. All right, let's move on. We're getting into some acid. It says sulfuric acid disassociates in water according to the following equation. Label the acid base, conjugate base. All right. Well, acids donates a proton, so it donates H plus. Base accepts H plus. I like to think of this kind of like a before and an after. The left side being before, right side being after. So if you look here, H2SO4 to HSO4, the only difference is a hydrogen. This will be our acid. This will be our conjugate base. H2O to H3O gains a hydrogen. This will be a base. This will be a conjugate acid. (15) says identify the conjugate base of HF. Conjugate base is going to lose or donate an H plus. So our conjugate base will be just F minus. So it lost or donated H plus. All right, calculate the pH of 0.25 molar solution of nitric acid. Here's what we want to see. Nitric acid is a strong acid. If it's a strong acid or a strong base, our calculations are relatively simple. So pH is equal to negative log of H plus. So we can just plug in our molarity. So negative log, because it completely disassociates, 0.25. And we do that on our calculator, you get 0.60. Done. All right, calculate the pH of a 0.003 molar solution of NaOH, and it tells us NaOH is a strong base. Strong acids, you can just plug straight in. Strong bases, there's a little bit more work. So we're not finding pH, we're finding POH when we do our negative log. So when we plug in, it'll be negative log 0.0030, and you get, let's see here, 2.5. From here, there's another step we have to do. pH plus POH equals 14. We don't know pH. We know POH is 2.5, and that's going to equal 14. So if we do a little bit of subtraction and rearranging, we get a pH of 11.5. 11.5 plus 2.5 is 14. All right. Calculate the pH. It tells us that we have a strong acid, but we have a number written in scientific notation. Hey, guess what? It doesn't matter if it's scientific notation. We just plug it in. So pH is equal to negative log 2.5 times 10 to the minus 6, and we get 5.6. Done. All right. 19 says, calculate the Ka value of a 0.2 molar aqueous solution of propionic acid, which is, if you didn't know, CH3, CH2, CO2H with a pH of 4.88. Okay, here. So we are going to need to do a Rice table because it's asking us for Ka. So let's start by doing that. we're going to need all of the values here. So we've got, let's see, CH3, CH2, CO2, H2O. Okay, so it tells us that we have 0.2 molar of that. H2O, it doesn't tell us in the question, but this is a liquid, so we can actually cross this one out. H3O is a 0, and this is a 0. Reactants go down, products go up, and let's combine. Okay. We don't have X, but what can we do here? We can get this value right here. Okay, we can get this value by doing the opposite of our, we can do the opposite of a pH to get this. So we can do base 10 minus 4.88, and that'll give us a value of 1.32 times 10 to the minus 5. Okay, now how was I able to do that? There's an equation. If you go on your equation sheet and look, we have an equation for H3O, and that is pH is equal to negative log of H3O plus. So if you see that, that's going to be the same thing as, we would approach that the same way that we would if we had H plus. Basically just plug it in to get your pH. So if we wanted to do the opposite and we wanted to find the value, we would do base 10, negative that number, and that would give us our X value. Okay, so we have that. So anything that's just X is going to be that value. So that means that H3O minus is going to be that value, which is 1.32 times 10 to the minus 5. Our CH3, CH2, CO2 minus will also be that number because it's just X. And our reactant CH3, CH2, CO2H is 0.2 minus X, which is that number. So when you do the math, when you subtract, you get 1.32 times 10 to the minus 5. All right, now we have all the numbers that we need to plug in and solve for Ka. Ka is products over reactants. The only two products that we have are going to be our H3O. Its value was 1.32 times 10 to the minus 5. And CH3, CH2, CO2 minus, which was also 1.32 times 10 to the minus 5, over our reactant, which was 1.32 times 10 to the minus 5. Plug that in your calculator, you get a value of 8.7 times 10 to the minus 10. A lot of big numbers going on. All right, we only have 2 more problems that we're going to work through. The last problem on our study guide deals with buffers, so we're going to skip that one here. All right. The dissociation of acetic acid has an equilibrium constant at 25 degrees of 1.8 times 10 to the minus 5. If the molarity of acetic acid is 0.920 moles per liters, what's the pH of the solution? All right, so there's a lot going on here. So what I would do is I would start, the question's asking us to find pH. pH is equal to negative log H plus. So if you go and look in the question, nowhere does it give us that. We don't have that. Okay, so that's a bummer. What else do we have in the question? Well, it tells us we have an equilibrium constant. I don't care that it's 25 degrees. That doesn't do anything for us. It gives us the equilibrium constant. So let's do a rice table and see what we can figure out. Anytime you have an equilibrium constant, a rice table is involved. All right. To write the equation for this, remember it's just losing a hydrogen. So it'll be CH3 COOH, and you'll have H plus, and then you'll have CH3 COO. So I guess I should have written that down here. Use a different color. All right. Molarity of acetic acid. Remember, moles per liters is the same as molarity. So it gives us this value, 0.92. We don't have an initial concentration of our reactants. This goes down. These go up. So 0.92 minus x, x, x. Okay, so we need this to be able to plug into our pH equation. And right now, it's just an x. So we need to find x. So it gives us the equilibrium constant. So Ka, products over reactants. So H plus CH3COO over our reactants, which were just CH3COOH. Okay, let's plug in everything we have. So we have our equilibrium constant. That comes right from the question. So 1.8 times 10 to the minus 5. H plus right now is just x. And CH3COO is also just x. And then in the denominator, we have 0.92 minus x. Remember, when you're working these types of problems and you have an x in the denominator, we assume this is negligible. Okay, so that's going to make the math a lot easier. So if we assume it's negligible, that means it's going to go away. So this is a lot easier to solve. Let's multiply both sides by 0.92. That'll go away. Okay, so you're going to get, let's see, 1.656 times 10 to the minus 5 equals x squared. We want to get x by itself, so let's take the square root of both sides. You get x is equal to 0.00407. Hey, guess what? We have x now. We can plug in. So that is going to be equal to h plus. So now we can go back to what we were trying to do at the very beginning, which was plug h plus into our equation. I am running out of room here, so I'm going to just erase this. So let's plug in what we have now. So negative log of 0.00407, and you get a value of 2.39. That was so much work. All right. we can do another one like that. So the next one is exactly the same thing. So it's asking us to find the pH, and it gives us the equilibrium constant. I don't care that it's at 25 degrees. And it gives us the molarity of our acetic acid. That should probably say cyanic acid. Interesting. Okay. Well, let's do a rice table. So we have HCNO. That's going to disassociate into H plus, and then CNO minus. Acetic acid. I think that means cyanic acid. That's got to be a typo. So it gives us 0.1. These are going to be 0. This will go down. These will go up. Okay. This will be 0.1 minus x. This will be x. This will be x. Okay. So let's go through and so remember when we're trying to find pH, we need this number right here. So Ka is equal to our H plus CNO minus over HCNO. Okay, so we don't have this number. We have an x, so we're going to kind of work backwards like we did in the last one. So it gives us the Ka, which is 1.0 times 10 to the minus 5. X times x is x squared over 0.1 minus x. Okay, minus x, but we assume that's negligible. Multiply both sides by 0.1. And let's see, you would get 1.0 times 10 to the minus 6 equals x squared. I will need to take the square root of this to get an answer here. Okay, so I actually don't have this handy, so let me just pull out my handy dandy calculator. So 1e 6 negative. And then we want to take the square root of that. Okay, so I get x is equal to 0.0316. And if I plug that into my negative log, I'm actually going to use a different calculator. Just a second here. All right, negative log 0.0316. And you should get, so if I take this, so this is equal to our x. So then negative log of 0.0316 is equal to 1.5. So pretty acidic. All right, 22 deals with buffers, and we are going to skip this one. It says rank the following acids from weakest to strongest. So smallest Ka to largest Ka. Now, when you're working with these, remember, if you have a negative power, that's a really small number. So this is the smallest. So it'll be C6H5O. Then this one. Then this one. then this one. And then finally our HCl, which is the biggest. And that's it. Wow. That was the most fun I've had all morning. Solid hour of just back-to-back chemistry. So there you have it. There's the entire study guide. If you have questions, reach out to your teacher. You totally got this. Good luck.